Hello students, in this video I am going to discuss about approximation algorithm to solve traveling salesman problem. So first of all you look at traveling salesman problem. Given a list of cities and distance between each pair of cities, what is the shortest route that visits each city exactly once and returns to original city. So here I have a salesman and he will travel some cities. So the ultimate aim is to find shortest distance to travel from one city to all other cities and come back to the city where he started. Here we have a list of cities and also the distance between each pair of cities will be given. So we are given a completed weighted graph. We find a tour, that is a cycle, through all the vertices of minimum weight. Here I have 4 cities, 1, 2, 3, 4, and distance between each pair of cities are given. So we have to find a cycle whose weight is minimum. And that cycle must include all the vertices only once. So for the given graph, the cycle 1, 3, 4, 2, 1 is the cycle with minimum weight. So important thing you have to notice it is a complete weighted graph. That means there will be an edge between every pair of vertices. And the minimum weight will be 15, 12, 25, 20. That is, the minimum cost to complete one tour is 72. Two greedy strategies are there. We already studied about greedy algorithm, nearest neighbor and shortest link. Both the greedy strategies give only approximate solution. Finding optimal solution is NP complete problem. So here we are going to study two approximation methods based on greedy algorithm, greedy strategy. One is nearest neighbor, next is shortest link. Approximation algorithm we already discussed, it will give the near optimal solution. Approximation algorithms are relevant because finding optimal solution is an NP complete problem. NP complete also we have discussed in the previous videos. So this is example for nearest neighbor strategy. First step is select an arbitrary vertex S to start the cycle C. So here our aim is to find a cycle which contain all the vertices, and also in the cycle the vertices will appear only once. So you can choose any vertex as a start vertex. Here I am choosing start vertex as 1. 1 is included in the cycle. V equal to S, so V equal to 1. While there are vertices not yet in C. Now C contain only one vertex, that is 1. 2, 4, 3 are missing in C. So this while loop is true. So select an edge V, W of minimum weight where W not in C. So V is 1. So we have to find the vertex whose weight is minimum, which is starting from vertex 1. So from vertex 1, the edge 1, 3 is the edge having minimum weight. And 3 is not in C. So I can choose 1, 3. So I select 1, 3. 3 is included in the cycle. Add V, W to C. V equal to W. So now V equal to 3. While there are vertices not yet in C, 4 and 2 are not in cycle. So this condition is true. Select an edge V, W of minimum weight where W not in C. So now we have to choose the vertex from 3 having minimum weight. From 3, the edge with minimum weight is 10. That is going to 2. 2 is not in cycle. So I can choose 3, 2. So select 3, 2. Add V, W to C. 2 is also included in the cycle. Then V equal to 2. Again, while there are vertices not yet in C, vertex 4 is not in C. So we have to find the minimum edge from 2. So from 2, the minimum edge is actually 10. But it is going to 3. 3 is already in cycle. So we can't consider that edge 2, 3. Next, we have to look at the next smallest edge. The next smallest edge is 20. But 2, 1 we can't choose because 1 is already in cycle. Next largest edge is 25. That is going to 4. 2, 4. 4 is not in the cycle. So we can choose 2, 4. So select 2, 4. Add V, W to C. 4 is also added to cycle. V equal to 4. Add edge V, S to C. S is chosen as 1. So I have to add 4, 1 to cycle. So 1 is also added to cycle. So I got a cycle 1, 3, 2, 4, 1. So from 1 the salesman started his tour and he comes back to 1. So the total cost of tour is here 85. So it is not giving optimal solution. We already studied optimal solution for this problem is 72. But it gives some nearest optimal solution as 85. Next is shortest link strategy. Similar to Kruskal's algorithm for minimum spanning tree, we are constructing a cycle rather than a tree. Grabs the lowest weighted edge from among all remaining edges anywhere in the graph. There must be no cycles before we are adding last edge. No vertices incident with more than 2 chosen edges. So these points will be clear once we saw the example. So this is the pseudocode for shortest link traveling salesman problem. The same example I have chosen. The first step is R equal to E, where R is the remaining edges. So R is a set which contains all the edges. These are the edges. One thing worth noticing is, since it is an undirected graph, 1, 2 is same as 2, 1. Similarly, 2, 1, 3 is same as 3, 1. C equal to null. Initially, cycle is null. Here also our aim is to find the cycle with minimum weight. Here the condition is while R is not empty. Anyway, R is not empty. Remove the lightest edge V, W from R. Here the lightest edge is 2, 3. That means we are looking at this in this R. 2, 3 is having the lightest edge. So remove 2, 3 from R. So this is R where 2, 3 is missing. If V, W does not make a cycle with edge in C, and V, W would not be the third edge in C incident on V or W. So anyway, our cycle is null. So V, W does not make a cycle with edges in C. C didn't have any edges. So this condition is true. Add V, W to C. So 2, 3 is added to cycle. Next, while R is not empty, we have to choose the lightest edge from this set. From this set, 3, 4 is the lightest edge. 3, 4 is the lightest edge. The 3, 4 is not making a cycle with edges in C, and also it is not making any third edge in C incident on V or W, and V, W to C. So 3, 4 is also added to C. So again we will check while R is not empty. Remove the lightest edge V, W from R. So the next lightest edge is 1, 3. So it is removed. Then I am checking the condition whether 1, 3 is making a cycle with edges in C. C contain 2, 3, 3, 4. 2, 3, 3, 4. Next I am considering 1, 3. 2, 3, 3, 4. I am trying to add 1, 3 also. Anyway, it is not making cycle. So the first part of this condition is true. When you look at the next condition, would not be the third edge in C incident on V or W. So here our edge is 1, 3. This 2, 3 and 3, 4 is already in cycle. Actually this 1, 3 is a third edge which falls on 3. So we can't include 1, 3. So I hope you understood the meaning of the second point. Actually 1, 3 is incidenting on 3 as a third edge. So we can't add V, W to C. That's why nothing is added to the cycle. Again, R is not empty. Remove 1, 2 from R. So here 1, 2 is the next lightest edge. So 1, 2 is not in R. 1, 2. Already 2, 3, 4 is in the cycle. So I am trying to add 1, 2. It is not making any cycle and it is not making any third edge. So 1, 2 is added to the cycle. Next lightest edge is 2, 4. Remove 2, 4 from R. We can't add 2, 4 because 2, 3 and 4 is already 2, 3, 4 is already in the cycle. If we try to add 2, 4 also, it is making a cycle. Here, if we had to check whether V, W does not make a cycle. Actually, 2, 4 is making a cycle. So the first condition itself is false. So we can't include V, W to C. So only remaining edge is 1, 4. Remove 1, 4 from R. 1, 4 is the next lightest edge and only the remaining edge. So based on this condition, if I try to add 1 comma 4, it will make a cycle. Based on this condition, the line 5, if I try to add 1 comma 4, it will make a cycle. So I will not add 1 comma 4 to C based on step 6. But you look at line number 7, add the edge connecting the endpoints of path in C. So now C contains 1 comma 2, 2 comma 3, 3 comma 4. Add the edge connecting the endpoints of the path in C. Now I have a path 1, 2, 3, 4. 1, 2, 2 to 3, 3 to 4. Based on this statement 7, I am adding 4 comma 1 to cycle. So now I got a cycle. Now R is empty. So this while loop will not execute anymore. So cost of tour is 20 plus 10 plus 12 plus 35, which is equal to 77. In the earlier case, we got the output as 85. Here we got the output as 77. Actual optimal solution is 72. Here we got much nearer value. So I hope you understood approximation algorithms for traveling salesman problem. Thank you.